Okay, so we're going to start off with well, these are the key concepts. So we're basically going to start off talking a little bit about what diffusion MRI is. We're going to talk about something called the B-value. And we're going to talk about how just using diffusion-weighted MRI is useful for certain things. But then we're going to sort of go on to differentiating between what's called isotropic and anisotropic diffusion. Talk about diffusion gradients, diffusion tensor imaging, what you can measure with DTI, and then track-based spatial statistics. All right. And then if for next, on Wednesday, we're going to get into more things like high angular resolution diffusion imaging, multiple B shells, get you up to speed in terms of what are the latest protocols that, for example, the large consortium studies are using. Okay. So we're going to start off with a movie. Hopefully this works. Yes, it does. So this is basically what's happening in diffusion. So we start off with the particles in one place, and over time they diffuse. Okay? And it turns out that MRI is highly sensitive to this process. Okay? So I'm not going to go through the math here, but the idea is if we think about, it's typically given the name a random walk. Okay, so in 2 dimensions, if you start off here, at some point, the particle essentially goes on a random walk. Okay? And if you looked at a number of particles over time, they would spread out. All right? In 1D, this is sort of the number of steps you take. So this is the typical examples if you get drunk in a bar, you know, in Pacific Beach or something, and you wander out, you do sort of a random walk. Okay? And that's sort of a good analogy for diffusion. And so just to give you a sense of what sort of spatial scales we're talking about, so the diffusion of water is close to 2 in units of micrometers per second, micrometers squared per millisecond. It doesn't really matter what the units are. But the typical time scale of MRI that we're looking at is on the order of 10 to 100 milliseconds, all right? Very short time scale that we're trying to measure things in, okay? And so you use this formula. So this formula is saying how far on average does a particle move if it has that amount of diffusivity or diffusion and then in that amount of time, and only moves about 20 microns. Okay, and so if you change things a little bit, maybe it's 20 to 40 microns, depending on the D value, which is the diffusivity, and how long you wait. But what it's saying is that the MRI, because it's sensitive to diffusion, we're able to make the MRI sensitive to movements that are on the order of tens of microns, which is pretty incredible. Okay, so that's what we're looking at. This is just showing, once again, that that's that formula again, and showing that the distribution essentially, as we go from 1 millisecond to 2 milliseconds to 5 to 10 milliseconds, basically things just spread out. Okay. So Albert Einstein was one of the first to derive, or was the first to derive some of these equations. And so essentially this mean square displacement, or how far a particle moves, is related to the diffusion coefficient, how long you wait, and also the number of dimensions. Okay, so 1, 2, or 3 dimensions is typically what we think about. So that's just showing that in 1D, the formula is square root of 2 dt. In 2D, it's 4 dt, and in 3D, it's 6 dt. Okay, so that's just the basic picture of diffusion. So even though I haven't told you anything about what causes diffusion, I think you can all take a good guess at this question. So let's just give this a try. So I'm going to publish this question now, and go ahead and take a look and see if you can sort of. So the question is, diffusivity is highest in which of these tissues? Gray matter, CSF, white matter, skull, or scalp? Okay, so just based on what you think diffusion is, just take your best guess at that answer. Okay, it's exactly 50-50. So 50% of you pick CSF, 50 pick white matter. Okay, so one of those is the right answer, so that's good. For those of you, so let's try to think about what might be some reasons for each of these tissues. So someone who picked white matter, why would diffusivity be highest in white matter? Or even if you didn't pick white matter, you can argue for that side. Any thoughts?
It's the connections between neurons. So there's a lot of molecules that are being transmitted across different.
Right. That's basically diffusion should happen pretty easily along the nerves. So that would be a good reason. Okay. How about CSF? Why would CSF be the most have the most diffusion? So CSF stands for cerebrospinal fluid. Okay.
Because there's not a lot of structure to inhibit the diffusion process.
Right.
It could spread more freely.
Right.
In a fluid medium.
Yeah. So it's basically almost close to water, right?
Yeah.
Okay. So it turns out diffusion is higher in CSF, okay, because it's the least restricted, the least inhibited. So it's pretty much like water. But it is true that along the white matter tracks, there is better diffusion than against, and that's what we'll talk about. Okay. Any questions on that? Okay. All right. So the next thing we're going to do is we're going to review gradients. What are gradients? And we talked a little bit about that in the first lecture, I believe. And on an MRI machine, we have an X gradient, we have a Y gradient, and we have a Z gradient. Okay. And basically, that's just changing the magnetic field as a function of either X, Y, or Z, the strength of the magnetic field. And remember, the key thing with gradients is that it makes, if I have a gradient, so in this case I have a gradient along the X direction, so it's stronger here and it's weaker here, it's a linear gradient. So a spin that's sort of out here is going to process faster than a spin that's in the middle, and then a spin that's over here is going to process slower. Okay, so the gradients cause spins to process at different rates. And that's going to be important for getting sort of an intuitive understanding of how diffusion works. So this is sort of a toy diagram of that. So imagine we've got two spins, okay? And we've applied this gradient here, okay? And then imagine these spins, we're going to keep this gradient on for a certain amount of time, and while that gradient is on, those spins can move around, okay? So one of this guy went this way, and this one went that way. Okay, so they're moving around, and we're mostly concerned about the X direction here. Okay, so this gradient has moved, this one has moved into a place where the field is much weaker. Okay, and so it's going to sort of lag behind much more than this one will, which lags behind a little bit, but it's only experiencing sort of a relatively less weak field. Now what we're going to do is we're going to apply the gradient. So let's say we did this for like a millisecond, right? If we then come around and for the next millisecond, we apply gradient in the opposite direction, okay? Then if the spins were stationary, we would just rewind the phase and they would both be back at their starting position, okay? But instead, they keep moving around, okay? And so they don't rewind completely. And so they end up, what the bottom line is, you end up with the spins having different phases, okay? And remember, if you have spins with different phases, it's like adding vectors with different directions. They're going to tend to cancel out, okay? And the more we wait, the more those spins will get out of the phase, the more the signal will go down. Alternatively, if we make those gradients stronger, such that they really, as they're moving, they really move into different parts of the field, the signal will go down faster. Okay, so that's the intuitive idea. We'll talk about how we actually implement that, but that's the basic idea. That's why diffusion imaging works, because basically when spins move around randomly, they're experiencing different fields, and then when we try to reverse that, they keep moving randomly, so they never get refocused. All right, and also because they're moving randomly, each one experiences a different kind of dephasing. So overall, the signal is going to go down. All right. So the main thing to realize is diffusion causes the MRI signal to go down because of this dephasing. This is a picture from a really good book on basics of diffusion imaging. So here it's showing the gradient here. We're showing in one case the gradient is positive, and then at some point in time we make it the other way. And so if the spins are not moving, then if they're in phase at the beginning, they'll also be in phase at the end. Okay, so there's no diffusion. If you apply a waveform like that, then whatever this gradient does to make the spins go one way, this gradient can reverse and make the spins go the other way. Okay, so without diffusion, there's really no signal loss. Okay, in this ideal picture. Now with motion, okay, now all of a sudden, basically, let's say these spins in the yellow move around, then at the end, they are out of phase with respect to all the other spins, okay, because they've gone and experienced different parts of the field and they're not fully refocused. And so there's going to be a signal loss overall when we sum up all these spins. The sum of all those spins is going to be less than if they were all aligned. Okay. This is yet another picture from another article showing, so this is without diffusion. So in a gradient field, you see the spins sort of get out of phase, right? But if they're not moving around, and so I apply this gradient here, they get out of phase, and they sort of keep that phase, and then after I apply this rephasing gradient, they're completely rephased. Okay, so they're all in sync, so the signal is strong. In this case, we start off with them all in phase, we dephase them, okay, but now this guy moves over here, okay, so it's basically, when it comes to be rephased, it's not going to get rephased the way it should be, and so it's going to be out of phase, so the sum here, once again, is less. All right, so this is just to try to get it across, why diffusion weighting actually works in MRI. It's all about the phase of the spins. Okay. Any questions? Okay. All right, so that's about all the MR physics we're going to do. Okay, everything else is just sort of what do we do in terms of applying this to get images. So we've been talking about these very simple things where it's dephasing and rephasing, and this is what's called sort of bipolar gradient. Okay, so if you heard the term bipolar gradient, it basically just means it's going up for some amount of time and then equal and opposite going down. Okay. Now, what we talked about either in the first or second lecture is if you just do a scan like that, because there's a lot of other magnetic field homogeneities on, this is what's called a gradient echo image, right? You're going to end up with like dropouts in your signal. Okay, so when you do fMRI, for example, oftentimes you'll see dropouts in the signal towards the front of the brain, right? In diffusion imaging, it turns out we don't need that T2 star contrast, right? We're not trying to measure T2 star. So what we can do is we can use a spin echo. Okay, so we have this refocusing pulse, which gets rid of those homogeneities such that we end up with that nice sort of, the dropouts go away that are due to the static homogeneities. The tricky thing is, though, because this refocusing pulse changes of the phases, now the bipolar pulse just becomes, it's symmetric around the 180. Okay, so even though we talk about bipolar gradients quite a bit, when there's a 180, then they're actually the same direction. Okay, so that's just something to know. And actually what's used in practice from almost all modern fMRI, say HCP or ABCD, is actually what's called a dual spin echo. Okay, so there's two 180-degree pulses. It just turns out that this has slightly better properties for handling what are called eddy currents, which we'll talk about next lecture. So this just has been sort of adopted by the field. Okay, but it's the same principle. Essentially, these gradients here are what causes diffusion weighting. Okay. Yes, question.
So the dephasing is being measured by the negative part of the y-axis?
This dephasing?
Yes.
Yeah, that's basically sort of saying how much dephasing there is. Yeah. So yeah, this. So if you look here, sort of, if we go here, all the dephasing is happening like that, right? So it's just showing that the phasing of the spins is, as I increase the gradient, I increase the dephasing, and then I just keep that amount of dephasing between the gradients, and then I'm rephasing it here. So the idea is things have to start here, go up, and then go to 0. And during this whole period, if things are moving around, that's the motion I'm capturing. Okay? Okay, so the next thing we want to talk about is the b-value. Okay? So it turns out that the signal I measure is proportional to the exponential of minus b, where b is the b-value, so this is the b-value, times d, which was the diffusion coefficient. Okay? And it turns out that the b-value is proportional to gradient area squared times the diffusion time. All right, so what is the gradient area squared? That's just sort of this area here. So it's like g times delta squared. Oops, sorry, g times little delta squared. Okay, so that's the bigger I make that area, the more dephasing there's going to be, and so the signal is going to go down faster. The other thing I can play with is the distance, the delta between the gradients. Okay, because if I apply gradients here and then I wait a long time before I rephase them, they have all this time to get out of sync. Okay, so those are the two factors. But for most of the experiments that you will be doing, the b-value has already been decided for you by somebody else and designed for you, or the manufacturer has all these b-value calculations. So whatever you set, if you ask for a b-value, it will just figure out the gradients and timing for you. Okay, so it's not typically something you need to worry about. The main thing you need to know is that the signal goes down exponentially with b-value. Okay, and that's shown here. Can you get the lights? We're going to be showing some images, so it'll probably be a little better. Okay. So here's an example of b-values, and these are, in most of the scans you'll be doing, there's always going to be a b equals 0 image. Okay, so this is essentially the image without additional diffusion weighting. Does it have no diffusion weighting? No, there's always some diffusion weighting because there's always gradients in your pulse sequence. But it has what we're calling minimal diffusion weighting. So that we're calling this the b equals 0 image. Okay? The actual b-value might be 2, 3, or 4, but for all intents and purposes, we're calling it 0. And then as you can see, from 300 to 1,000 to 2,000 to 3,000, that signal level is just going down exponentially. Okay? And just to give you a sense of what's used in practice, for example, the HCP protocol typically uses between 1,000 to 3,000 and picks different b-values between those. Okay, so on Wednesday we'll talk about why would you pick multiple b-values and directions, but for today, just showing you what the effect is on b-values. So the good thing is, the higher the b-value, the more diffusion contrast you're going to get, but the problem is you're also killing your signal. So there's always this trade-off between the more b-value will tend to make things look different according to the diffusion properties, but it's also going to, at the same time, your signal is also going away. Okay, so this is just an example of a very common way of changing b-values. So for example, this is a spin echo image, a spin echo pulse sequence, and in this case, we're just increasing the amplitude of the gradients. Okay, and so as we increase the amplitude of the gradients, the area is also going up. And so the b-value is also going up. And you can see here, as we do that, these values are also going down. So typically when you're doing an MRI pulse sequence and they're changing the b-values, for example, in the HCP or ABCD protocol, this is what they're doing. They're just changing the gradient amplitudes, okay, and making the b-value stronger or weaker. So this would be the b equals 0 image because there's no added gradients. Okay, so why is this useful? Well, for one thing, that different tissues have different diffusivities. We already talked about how, for example, CSF is higher than white matter. Okay, And especially in clinical applications, that's actually very useful. So in this case, you're looking at images across different B values. Okay. And if you look at sort of where the magenta dot is, you can sort of see its signal value around it's dropping quite dramatically. Okay, so it's showing this decay here. Okay, whereas for the blue dot, I'm not sure the color's sort of different, but the cyan and the dark blue are the same. If you look at that, the signal level is staying fairly constant. Okay, so from this we can come up with a map of what the diffusivity is. Okay, and so here we can sort of see that around here it's fairly black, so it's saying that the diffusion there is relatively low, and this is in a relatively higher area, and diffusion there is higher. And then notice in CSF, very high values. So lots of diffusivity in the CSF. And if you notice the CSF in these images, that signal basically disappears quite rapidly with B value. Okay, so that's what's going on there. Okay, so typically what people do is, you have these different B values, and so you can measure the signal, and you can sort of, it's going to follow some exponential decay. Okay, but if you want to sort of actually fit for these values, then what we'll typically do is take the log of both sides, and so we have log of S is equal to log of some constant minus BD. Okay, so the slope of this line is just minus B. Okay, if I plot the log of the signal versus the B value, D. Let's get the eraser here. So the slope is minus D. Okay, so the log of the signal is a function of B, has a slope of minus D. Okay, so we can just solve for the diffusivity. And so in this case, in this table, they've increased the gradient amplitude. They've kept the timing the same. You see the B values are going up. Okay, and then they measure the signal here. They take the log of the signal, and then they fit for the line. And if they fit the line, they find that the diffusion is about 2 times 10 to the minus 3, which is basically the diffusion of water at room temperature. Okay, so that makes sense. So this is just to show that if I have measurements and multiple B values, I can come up with an estimate of diffusion coefficient for every voxel. Okay, so that's the most standard way of diffusion-weighted imaging. You just apply different B values, and you try to measure the diffusion at each voxel. And so this is what you end up with. For example, this is a T2 weighted image. Oops. Here. Okay. This is a diffusion weighted image. Okay. So this is showing they've applied some diffusion weighting, and so the signal in this area of the brain has gone up quite a bit. Okay. And if you notice the T2 weighted image, it really doesn't show much at all. Okay. So what's happened here in this area where the signal has gotten really bright? Has diffusion gone up or down in that area of the brain? Down, right? Because remember, our signal is e to the minus BD. Okay, so if the signal is brighter, we're assuming the B value is kept constant. That's determined by the pulse sequence. So if the signal got brighter, then this D value must have gone down. Diffusion has to have gone down. Okay, and so that's actually shown here in this diffusion map. So this is called ADC map, which is what stands for apparent diffusion coefficient. Okay. It's just saying that there's a lot of factors that go into the actual D value. So this is just sort of the apparent value that we measure. And so that's showing there that that's gone down. Okay. So this is another set of images. So you can sort of see here in the T2 weighted images, there is something going on here if you compare the left versus right. I mean, there's obviously something going on with this person's brain. If you look at the diffusion weighted image, you clearly see that it's much brighter. Okay, so diffusion has gone down in this person's left hemisphere. And if you look at the angio, clearly their blood supply, so this person had a stroke. Okay. Now, this has been known for probably 30, almost 40 years since this observation, since the early 90s. Okay, and it's used clinically. I mean, if you have a stroke, you will definitely, most likely, if you don't, if you most likely you'll get a CT, but if there's time, they will give you an MRI. And diffusion weighted image is currently part of the standard of care. But the exact mechanism for this still aren't clear. It is known that the diffusion goes down, and it's thought that it's related to the fact that let's say with cell swelling or something, maybe the diffusion between cells is reduced. There's also thought that maybe a lot of diffusion in cells is due to mechanical motors actively transporting water, and maybe those have died. And so really the causes of that are still under investigation. But clinically, it's a very, very consistent result. If you have a stroke and there's brain death, if there's tissue damage, you will definitely see diffusion go up. Yeah.
Is that right in the acute phase of the stroke? Once it becomes stabilized and you have that damaged tissue with CSF increase, then would you expect later on to see more of an increase of diffusion since you do have more CSF filling
Yeah,
up?
it really depends on how the necrosis works, right? If it fills up with CSF, then you're going to have partial voluming. But if it, basically there's sort of the core of the stroke, and then there's also the penumbra, which is sort of, whether that area can be revitalized or not. The latest seems to suggest that if you have your vessels unblocked early on, that can reperfuse some of those regions. But yeah, I think what happens in terms of how much CSF gets in there varies quite a bit, but it's something to keep in mind. And in which case, you can apply things like potentially you can null out the CSF before you could do FLAIR diffusion weighted image or something like that. Or you can get an estimate of how much CSF is in there with another scan and then use that to interpret your studies. Okay, great. Okay, so this is the next question, and the basic idea is, let me open it up first. This is question 2, right? Okay, so here we have 4 different pulse sequences. They're all spin echo. And all I've really varied is, you can sort of see we're varying sort of the distance between the gradients, how long we play them out for, or how big they are. And so you have the different options. You can say whether this has more diffusion weighting and less T2 decay, or more diffusion weighting and more T2 decay, or less of both, or more or less. So actually 2 of those answers are the same. So your chances of being correct are slightly higher than 25 by chance. Okay, so go ahead and feel free to discuss that with your neighbor. Just trying to get you to start thinking about how the pulse sequence is related to what actually happens. Okay, let's take a look at this. So let's start off with sort of, so if we think about, if we look at these four pulse sequences, which of these pulse sequences has the detection time at the latest point in time? B, right? So B does not look like the others, right? That's like, which one of these things doesn't look like the others, right? So that's always a good strategy for these problems. So that's got the longest echo time, right? So that's going to have the most T2 decay, right? Because remember, there is a T2 decay that's minus TE over T2. So there's only one answer that has more T2 decay. So B must go with 2, right? Okay. Everyone okay with that? Okay. So now let's look at the answers on the left-hand side. So we've got more DW, less DW, more DW. So there's only one that must have less DW, right? So which one of these doesn't look like the others? A, right? So A's not been modified at all, right? And in fact, let's compare A to everything else, okay? A compared to B, B increases the distance between the diffusion gradients. So there's more time for things to get out of phase. So that's going to have more diffusion weighting. C increases the area of the diffusion gradients. So that's going to cause more dephasing. So that's going to have more diffusion weighting. And G increases the amplitude. So that's also going to have more diffusion weighting. So A will go with 3. Okay. And then 1 and 4 are the same answer. So whether you pick C or D doesn't really matter. Okay. They both are going to increase the diffusion weighting, and they have the same T2 decay as A. All right. Good. Any questions on that? Okay. So that's just giving you a general feel for why there's when they say the MR physicists or the engineers are monkeying with the pulse sequences, this is sort of the thinking that they're taking into account. Okay, so we're going to switch gears here now, and so far we've really implicitly been talking about isotropic diffusion. So in water, We call it free diffusion or isotropic diffusion, where you just imagine the particle can go anywhere it wants. Okay. In biological tissue, that's not usually the case, and especially as was alluded to before, in white matter, there's what's called anisotropic diffusion. Okay. So there's a preference for diffusion to go along one direction typically, and in the white matter, it's typically along the direction of the fibers. Okay. And so here, we're going to end up with what are called sort of diffusion ellipsoids or diffusion ellipses. Okay, so we're going to represent diffusion as instead of the spread being sort of circular, it's going to end up being ellipsoidal. This is just a movie to sort of give you a sense of what that. This is a simulation that someone on the web did, and so you can sort of see that those orange particles are sort of stuck, right? And now you're seeing this path of an orange particle on the left-hand side there. And you sort of see that it's basically whenever it hits a boundary, it just comes back. Okay, so that's restricted diffusion. It can't get outside of its barrier. Okay. So what we want to do you can see it can go more easily along the length. Okay, so this is what we want to sort of, and there's more to that movie if you want. I mean, he's got lots of movies, so you can watch all these simulations if you want to. But I think that gets the point across. That essentially, there are sort of barriers in biological tissues, and that's going to restrict diffusion. And so, as we alluded to before, it's going to be much easier to go along, a fiber than against a fiber. So here, this particle is really stuck. It can't get out of there, but it can diffuse quite easily along the longitudinal direction of the fiber. So that's basically what we're looking at. We're basically saying that, we're comparing free diffusion where things can go in any direction versus anisotropic diffusion where now there's some restriction due to the biological tissue. So the next thing we have to think about is how do we actually measure that? Okay, and the idea now is in addition to just applying the gradients, we want to apply gradients in different directions. Okay. So let's say here we apply a gradient in the horizontal direction, so the field changes in the x direction. This is going to be sensitive to any motion in the x direction. So if there's diffusion along the x direction, loss. If there's diffusion in the vertical direction, it's going to be relatively insensitive to that. So to first order, there's no signal loss. Okay. If now we do a vertical gradient, okay, then if there's motion in the x direction, there's not going to be, to first order, any signal loss. But if there's motion along the diffusion direction, there's going to be, along the gradient direction, there will be signal loss. Okay? Because basically, if it's moving along this direction, it's sampling different fields, right? Whereas if it moves in this direction, it's not sampling different fields. Okay? So that's the basic idea. So here's an example of here. This is showing which direction. In this case, the gradient was applied in the left-right position. And you can sort of see here on this dot where they're emphasizing there's a signal loss. Okay? So there's some diffusion there connecting the two hemispheres. Notice if they apply the gradient in the anterior posterior, the signal is recovered there because there's no diffusion going in that direction at that point. Okay? And then this is showing a diffusion gradient sort of perpendicular to the plane, so in the z direction. And you can sort of see here, there's no signal loss there. Okay, so the basic idea is signal loss, if I apply a diffusion gradient in one direction, then wherever I see signal loss tells me that there's diffusion in that direction. Okay, if I apply it in another direction, that tells me about signal loss in another direction or diffusion in another direction. So here's another example. Here we apply the gradient left to right, and you sort of see there's quite a bit of signal loss there. Here I apply the gradient sort of in the xy direction, and so you sort of see here a lot of signal loss on this side, but not so much signal loss on the other side. Okay, because the diffusion, this is picking up the diffusion here, but it's insensitive to the diffusion in that direction. Whereas if I do something in the x minus y direction, now you see signal loss here, but not so much over there. Okay, so you can sort of see if I just apply different directions, I can slowly build up this picture of which way the diffusion is going. Okay. And in this case here, when I apply the diffusion gradient perpendicular to the plane, you sort of see there's really no signal loss, saying that the fibers are running left, right, AP, but they're not running in the inferior superior direction. Okay. And so you can sort of see here, if I sort of built up that picture of which way the diffusion is going, I can start mapping out, what that fiber is doing. All right. So typically, there's a lot of anisotropy in the white matter and relatively less anisotropy in the gray matter, and definitely not in the CSF. Okay. Unless there's something different about the CSF due to a disease state or something. Okay, so a typical diffusion sort of tensor protocol is going to do the following. There's going to be at least one B equals 0 volume, okay, because that allows us to figure out how much decay there is. But then there's going to be a lot of different directions. Okay, so in this case, they've acquired 60 different volumes. Probably each volume is in a different gradient direction. Okay, and so you can sort of see here in CSF, there's a big drop in the signal from B equals 0 to applying the diffusion weighting. Okay, so that's because CSF has a lot of diffusion, but there's very little sort of difference in the signal as I'm going along different directions because the diffusion is relatively isotropic. Whereas here in white matter, the signal drop is not as much because the diffusion in white matter isn't as high as in CSF, and yet you're seeing a lot of sort of variation in that diffusion signal. And this is probably just for one voxel because depending on which way the gradient was set up, it was either aligned with the diffusion or not aligned with the diffusion or at some other angle. Okay, so now you have enough to do this problem. So once again, it's sort of matching, and what you are shown here are actually 5 different images with different options for diffusion direction or else a B equals 0 image. Okay, so go ahead and take a look, discuss it with your neighbors, and we'll regroup in a bit. Okay, let's take a look at this. So you've got 4 different gradient directions, and then one b equals 0 image. Okay, so let's start out to figure out which of these must be the b equals 0 image, and why. Any guesses? So remember, what tissue has the highest diffusivity? CSF, right? So it's going to be the brightest on the b equals 0 image. Okay, so there's no diffusion weighting applied to that image. So it's going to, and also, although we didn't talk about it today, we did talk about it maybe on Monday or on the first lecture. CSF has the longest T2. Okay, so these are typically the b equals 0 image. The way you can identify it is it always has really bright CSF. Okay, because otherwise, now it's sort of a trick question because everything's been scaled here a little differently, right? I mean, the overall image is darker, so you would think maybe that's not the b equals 0 image, but where I copied it from, they obviously auto-scaled it, okay? But if there was any diffusion weighting applied at all, you wouldn't see the CSF. It would be very dark, okay? So the fact that you see CSF means it must be the b equals 0 image, all right? So we'll just match that with that. Okay, now let's look at which of A, B, C, and E is not symmetric? C, right? C is obviously not symmetric. So what must C go with? 4, right? Because obviously it's got diffusion, it's sensitive diffusion in that direction, and you sort of see that it's dark for that fiber, but not dark for the symmetric fiber. Okay, so that's good. So what about B? Is it dark along the fibers running AP or left to right? Mostly the AP fibers are dark, right? So that must be this one here because it's sensitive to diffusion in that direction. Now we're down to A and E. Which of these has diffusion weighting that's obviously affecting the signal? E, right? So E is obviously sensitive to this left-right. And by process of elimination, this is always a little hard to tell because there might be fibers running that you can't see. So it's more like by a process of elimination, that's the only one that has the least amount of obvious diffusion weighting in plane. Okay? So typically you don't have to deal with this, but it is sometimes useful to look at your diffusion images, and once in a blue moon, things do get messed up. Maybe there's some problem with indexing or something. So it is useful to be able to sometimes do a sanity check of your images and just make sure it's the B directions are corresponding to the actual images you're getting out. Okay. Any questions before we move on? Yes.
So, in these images, really, where we can see this is within the CSF, but
for the b equals 0.
Where there's a lot of variety between the images for the CSF, right? That's kind of where looking at the brightness and.
You mean for D?
I'm just across all of them.
Oh, across all of them.
The point that we're looking at to see how it changes.
Actually, the dark spots in the other ones are in white matter. Yeah, so it is sort of tricky as you're looking at these images. You sort of have to keep. So across, if there is diffusion weighting applied, then most of the differences will occur along the white matter tracks.
Okay, and I think actually my question is kind of related to what you were saying earlier, because if someone has damage somewhere, it would also affect that area differently as well.
Right.
And it would depend whether or not CSF filled the space or if it's just.
Right. Well, if there's any diffusion applied, CSF will it's just not even there.
Yeah.
Because the signal is just gone.
Okay.
Because the diffusion is so high, typically.
Okay.
Yeah. So so that depends on the B value, right?
Yeah.
So typically, with the higher B values of say 3,000, I mean CSF is pretty much gone.
Okay.
If you used a smaller B value, then CSF would still be there. Now there are other issues where that there are issues of motion sensitivity and other things where potentially even if there was, the CSF signal would probably decay away much faster anyways. So I think to first order, whenever there's quite a bit of diffusion weighting applied, CSF isn't typically an issue. Yep. Okay. So that's a little different than sort of, because here we're not necessarily, we're looking at the directionality, right? Whereas this other question that you had asked was sort of what is the diffusion coefficient in that? So it's slightly different things that we're trying to ask, but related. Okay. Okay. So moving along, diffusion tensor imaging is then trying to sort of map out sort of what is the shape of the diffusion. And diffusion tensor imaging is sort of just trying to map out sort of what is the shape of the ellipsoid. Okay, so in 3D, it looks like that. And for this one, we would say the primary direction of diffusion is along the long axis of the ellipsoid. That's like the longitudinal axis of the ellipsoid. Okay. So this is, I'm going to show an equation just simply because you will hear the term diffusion tensor quite a bit. Okay. And all this means is now, remember previously we just said that S was proportional to minus B times D, okay? And where D was just the value, just the diffusion coefficient. Now D is going to be a tensor where it depends on the direction, okay? So instead of just one number, we're going to have 9 numbers. So it's going to be a matrix, okay? So just showing you that this is what the math looks like. The main thing is now this is now a matrix, okay, instead of a single number. And that's what we call the diffusion tensor. And this is what it looks like. It's got 9 numbers, but only 6 of them are unique because it's symmetric, because diffusion in the x, y, and the x, whether you go x to y or y to x is the same, and then x, z, and x, these are the same, and these are the same, okay? So there's only 6 actual unique numbers that you have to do for diffusion tensor imaging, okay? So the ones along the diagonal tell you about diffusion along the x, y, and z axes, okay? These off diagonals tell you about along the xy axis, the xz, and the yz. So there's just sort of 6 different directions that are sufficient to describe the ellipsoid. So to give you a sense of why that's the case, let's take a look at a 2D example. So in a 2D example, let's say that this was my ellipse that I'm trying to characterize. And if I can only measure in 2 directions, this fits the ellipse pretty well, right? Okay, but that can't be distinguished from this, right? These both fit those 2 measurements, but one is an ellipse that's slanted and the other is an ellipse that's sort of vertical. So it turns out I need, in 2 dimensions, I need 3 measurements to uniquely identify the ellipse. Okay, and what we're going to find out in 3D is we need 6 measurements. Okay. All right, so for diffusion tensor imaging, there's going to be those 6 measurements. That makes sense because there's 6 different unique elements of the diffusion tensor, plus we're going to add a b equals 0 image. So there's typically a minimum of 7 measurements that you have to do. Okay, and so the diffusion tensor imaging, DTI at the minimum, you need a b equals 0 image plus 6 directions. Okay, but what you'll find in practice is people do a lot more than 6 directions. They might do 30 directions or 40 directions, even though you only need 6. And part of the reason for that is every measurement you make has an error to it. So for example, if this was the true sort of ellipse, let's say we did a measurement here shown in red, which was wrong, then we would estimate a smaller ellipse here. Okay. Now we did more measurements, and they're all correct. We can sort of get that original ellipse as well. But even here, where all the red ones are sort of an error, because the error averages out over the directions, we can still get a pretty good estimate of our ellipse. So that's why, even though we only need 6 directions, typically, and even in a clinical protocol, you'll see many more directions. Okay? Yes?
Is there a trade-off with the number of directions in terms of like 230 or more? Like, are you trading off something? Or?
Yeah, it's always the more measurements you acquire, the better your image will. I mean, there's certain couple of trade-offs. One is signal noise ratio always goes up with more images because you can average more. The downside is the longer your scan is, the more motion there's likely to be. So, then you're just averaging signals at. If you can't correct for the motion, it could actually make your estimate worse. So typically, and then in clinical protocols, obviously, you're trying to go through as quickly as possible. if someone has a stroke, you're trying to get them in and out as quickly as possible. So typically you want to settle on a protocol that is as quick as possible, but gives you diagnostic information. Now for research studies, you often have more leeway, but there again, it depends on the subject population, right? If it's kids, you don't have that much time. If it's, grad students, you can keep them in there for quite a long time. Okay. Okay, so this is just sort of reminding us that for a three-dimensional ellipsoid, we need 6 directions. And the next thing we want to introduce, and the major concept is eigenvalues. Okay, so some of you may not have heard that term since linear algebra, but for diffusion imaging, it is something that's used quite a bit. So you'll have to get comfortable with that. The eigenvalues are essentially the length of those axes in the ellipsoid. Okay, so lambda 1 is always the principal eigenvalue, and that's always the longest length. And then lambda 2 is the next longest, and lambda 3 is the next. Okay, and so for the ellipsoid, you need the lengths of those axes, lambda 1, lambda 2, and you also need the directions, v1, v2, and v3. So these are your eigenvectors, and these are your eigenvalues. Okay. So the eigenvalues are used quite a bit in terms of figuring out how anisotropic things are, and then the eigenvectors are going to be used to tell you which direction the diffusion is going. So they're both actually going to be used. All right. So just to give you a sense of it, so this is what we want to measure, but these are in the axes. This is telling us diffusion along x, y, and z. And what we don't really care about diffusion along x, y, and z. We actually care about what's the diffusion along, what's the principal direction of diffusion in every voxel. Okay, and that's what the eigenvalues gets us. So we decompose our diffusion tensor into these eigenvalues and these eigenvectors, and that's just the expression. That's for those of you, if you remember in linear algebra, you might have remembered diagonalizing a matrix. So this is essentially that process, and it's useful because it tells you the directionality and also how skinny or fat that ellipsoid is. Okay. So just to give an example, if I have an isotropic voxel, that means the diffusion is independent of direction. So you would expect the eigenvalues to be almost all the same. Okay. If I have an anisotropic voxel, typically there's going to be one direction that has much more diffusion along it. So in that case, we expect lambda 1 to be much greater than lambda 2 and lambda 3. So the way we typically represent these things is sort of the radius of the ellipsoid tells us how much diffusion there is, the overall diffusivity. So CSF is the biggest one here, and it's isotropic, right? And then gray matter also has less diffusivity, but it's also fairly isotropic. And then white matter is fairly anisotropic and also typically has a directionality depending on where it is. Okay. This is just another picture of that. And so typically there is what are called prolate tensors, which are useful because they tell you directionality. And then there's something called oblate tensors, which happens when you have crossing fibers, right? Where there's actually 2 directionalities, right? And we'll get to this later, but this is going to give you an anisotropic tensor, but it's sort of, you can't really tell which direction the diffusion is going. So we'll deal with that on Wednesday, what to do with crossing fibers. Okay, okay, so this slide is just showing you that this is the same ellipsoid, just in different directions. Okay, notice that the diffusion tensors themselves are really quite different because they're giving you the x, y, z sort of information. But if you look at the eigenvalues, they're all the same. Okay, because these are all the same shape. Okay, so the eigenvalue really tell you something about the shape. And then if you look at these are the different directions. You see the directions are changing too. Okay, and so that's really, we're trying to take this thing, which is really not that useful to us, and convert it into parameters that are more useful. And then what we'll do is we'll use those parameters to make images. Okay. So this is just, these are actually the images I had in exercise 3. So that's where these images are from. So typically we have these images acquired at different directions. Okay. Each of these goes into making our diffusion tensor image, and that's what we're trying to estimate. Okay. So this is what we measure, and from those measurements we try to estimate our diffusion tensor. Okay. And just to give you a sense of what it is it turns out that it's just a general linear model. Okay, we line up all our measurements here, we take the logarithm of them all, and then it turns out we can solve for all those elements over there. Okay, so I'm not going to go through the math, but just to sort of say that the basic stuff we talked about in week 2, solving general linear models, that's what's happening under the hood when you're using something like DTI fit, a very standard tensor imaging. Now, if you do some more sophisticated analysis, it's going to be doing something more complicated than a GLM. But if you were stuck on a desert island and really had to do DTI, then you could just use a GLM. Okay. Okay. So now let's talk a little bit about what do we do with these eigenvalues. Okay. So there's really 2 main things that you're going to see all over the literature. Those are fractional anisotropy and mean diffusivity. Okay. So mean diffusivity is just the average of the x, y, and z diffusions, which is also equal to the sum of the eigenvalues divided by 3, which is the average eigenvalue. Okay, so this is the average diffusivity. Okay, and then we take that average, so this is the average, so this is the mean diffusivity, right? And we subtract each eigenvalue from that, and then we divide by the sum of the squares. And then there's these weird factors out here, so that it stays in the range from 0 to 1. Okay. A confusing thing in the literature is there's different expressions for FA, so you might see different people computing it differently. This is just from the Wikipedia showing you that there are just different things. Typically, you don't have to worry about this, but just if you're reading a paper and they give you a formula that looks different from another paper, it's just that mathematically all these things are the same. Okay, so let's take a look at what this looks like. So here's a weighted image. This is the trace, which is also equivalent to the mean diffusivity. This is the fractional anisotropy here. Okay, so notice the mean diffusivity is largest in CSF, which makes sense. We've already talked about how CSF has the greatest diffusion coefficient. But now that the fractional anisotropy is telling us how sort of, ellipsoidal or pointy each of the diffusion ellipsoids is, and you can sort of see here, you're really getting it mostly in the white matter. Okay. Now, there are other measures such as relative anisotropy and volume ratio that are also measures of how anisotropic things are. These tend not to be used as much in the literature, so we're not going to really talk about them so much. So really, primarily you hear about FA maps. Okay, and so for whatever reason, that has sort of taken over as the predominant measure. So, and then you can do lots of really fun things with FA maps. For example, this was an early study showing FA as a function of age, right? As the white matter develops, the anisotropy goes up and then sort of plateaus at some age, okay? As basically the white matter fibers are becoming more and more sort of defined. But as you can sort of see, and as people have talked about, it doesn't really stop until around age 25 for certain tracks, okay? This is looking at FA versus different verbal memory scores and recall and recognition in normal controls versus schizophrenia, and you're sort of seeing this sort of negative correlation between performance in FA, primarily in the schizophrenia population. Okay. And this was done where I forget whether this was done in mice or something, but it was looking at FA over a year. And what they found was in the white matter tracks, the FA went up, and in cortex, it went down, okay, with development. And so the idea here, the interpretation in this study was that there was increased myelination, okay, so that's going to lead to an FA increase, okay. But in the cortex, there was more mixture of fibers, okay, so there was sort of more sort of cells and the sort of different fiber orientations, and also more mixing of gray matter and white matter, and so probably FA was going down there. Okay, so that's just at least one interpretation, but that's just how an example of how you might use FA. This is an example, which is sort of a nice example here. If you look here in this region here, there's really not too much asymmetry in the diffusion coefficient. Okay, in this patient, this is a stroke patient, but you actually see quite a bit pronounced asymmetry in their fractional anisotropy. okay, indicating that there's some loss of anisotropy that's not reflected in pure diffusion change. Okay, so I think that's a good, we're going to end with this question, okay, just so you get a sense of how to work with these numbers. So on the left, you've got different eigenvalues, and on the left, sorry, on the left you have the eigenvalues, and on the right you've got the DTI metrics. This is question 4. Okay, let's take a look at that. So I think, so one of these has the FA of 0, right? And I think pretty much 100% agreement that that must be C, right? Because there's no, the eigenvalues are all the same, so there's clearly isotropic diffusion, okay? So that takes care of, and that has a mean diffusivity of 3. And then the only other one with the mean diffusivity of 3 is A, right? Because the average of 4, 3, and 2 is 3, okay, and that has an FA of 0.32. So now we have to think about which of these has a greater FA. Is it, they both have a mean diffusivity of 2, right? But clearly this one is more anisotropic, okay, so this would go here, and then this one goes here. And if we compare these two FAs, you know, the 0.32 versus the 0.46, we can see that going from a 3 to 1 is a 3 to 1 change, whereas going from 4 to 2 is only a doubling of change. So it makes sense that this FA is less than the FA of the 3, 2, 1. Okay? So that all holds together. So any questions on that? So that's just sort of basically when you're, so typically when you, and I think on the practical, you'll be looking at using DTI fit and FSL, you'll see eigenvalue maps that it'll spit out, but you'll also get FA maps, and this sort of helps you sort of try to understand the difference between, the relationship between those. So I'm just going to end with, let's see, let me just talk a little bit about a couple other things we'll look at, and then we'll end with FA. So the one thing to realize about FA is that different things can have the same effect on FA and mean diffusivity. And so a major problem with sort of, well, all of neuroimaging is the data we acquire are actually quite little compared to the complexity of the biological phenomenon. So it's ripe for overinterpretation, okay? So for example, if I have swelling, the mean diffusivity can go down and the FA can go up, right? Because basically now there's less room for the water to go through, and depending on how the swelling sets up, there might be a directionality to that. But I could also just have a higher density of cells that would give me the same sort of features. Similarly, if I had myelin loss, the mean diffusivity could go down, and the FA, or mean diffusivity could go up, because basically water can freely diffuse through the white matter tracks, even transverse, or else, but the FA would go down, okay, because there's less directionality. But I could also just have death of cells, okay, which may not be related to the myelin loss, which would give me similar effects. So there is some people will look at, compare longitudinal ADC, so a diffusion in the longitudinal direction, and compare it to transverse ADC, okay? And the idea is if there's a decrease in the longitudinal part, that's been interpreted as axonal death, okay? And if there's an increase in the transverse part, that's been interpreted as myelin breakdown. Okay. So this is an example of that here, where they basically looked at over several months in humans, sort of this decrease in the parallel diffusion, and they attributed that to axonal degradation, and an increase in the transfer that they're relating to myelin degradation. Now, granted, this is only 3 data points. There's a lot of interpretation that's going on in here, so whether this is true or not, it's sort of open to debate, but just to give you a sense of how people are using this data. Okay, so I think with that, we'll end for today. Are there any remaining questions? Great, see you on Wednesday then.